And I will at the same time share my screen. And you'll get this cascading effect here for a bit. So basically, we're still working on Unit 1 here, Introduction and Math Review. So we've done most of this other material here. Today we're going to be doing graphing. And inside this folder, you'll see there'll be the test, the math test, basically, for this. And that math test will be worth, by the time we meet next Monday, 2 o'clock Monday, it'll be due then. All right, so let me, first I'm going to go back to this so I can see what you guys are posting. No, the labs will not be in Blackboard. They'll be on Zoom. The labs will be on Zoom. Okay, so I think I'm set here. I can see if you guys post something. Move this over a bit. All right, so yeah, go ahead.
I'm sorry, I have a question.
Go ahead.
Would I need I've never used Zoom before. Do I have to make an account prior to the first day of lab?
I believe you don't have to. If you're going to join Zoom, you can just join it. You will get an email, and you click on the Zoom. You should be able to just join it. That's my understanding of how Zoom works.
Okay, I've never used Zoom, so okay, thank you.
Yeah, you will get an email from the instructor with a link to the Zoom. All right, so basically, as I mentioned before, next couple of weeks, actually, labs require you to make graphs. So that's what we'll be talking about. How do we make a graph from scratch? Why do we make a graph? So first of all, let me show you some graphs which are sort of timely here. So this is the number of COVID cases in New Jersey, and also this is the one on top is back in I guess August. It was in the summer time, the number of cases, and the one on the bottom here is in fact right now. It's as of January 2021. So you can see what's happened to the cases since August. The 7-day average over here. This is over here. The scale is different here because the cases have gotten so much bigger than the ones over here. So basically, that's an example of a graph. But the graphs that we make here are somewhat a little bit different because what we do is we want to find the connection, how things that we talk about in class are connected to one another. Usually they're connected by an equation. So let's start off with something simple. The things that you're changing, you're varying, are called graphing variables. For example, let's say I drop a ball from a certain height. The ball hits the ground. Okay, hits the ground and then bounces back up to a certain height over here. So let's say I drop it from a height of 75 centimeters, and it bounces back up to 25 centimeters. Okay, I say I do this a number of times, and I collect the data. So these are variables, things that I can vary, one of which I have control over. For example, the height of drop is my independent variable. I control it. And this is the dependent variable. It depends what this is. This depends on this is I have no control over the height of bounce. Now, the mission that we have usually is to find if two variables are related, and if so, how they're related. So I've actually chosen the data here very on purpose so that you can see how they're related. So for example, let me erase this. For example, we can see that they're related a pretty simple way here just by looking at the numbers, that this number for all of these values, this number is 3 times this number. So 3 times 25 is 75. 3 times 20 is 60. 3 times 15 is 45. So we know that the connection between these two variables is that the height of drop, height of bounce equals 1/3 the height of drop. It's a 3 to 1. Okay, and we get this by just looking at the numbers. We can figure it out. Okay, height of bounce equals 1/3 height of drop. But what if the data were different? For example, let's say we had this data. This would be more realistic data where you look at it and you say, you know, I can't figure out what the connection is by just looking at these numbers. So this is what happens when you make a graph. So in order to make a graph, first of all, you need graph paper. You have a piece of graph paper, and first thing you do on the graph, you label the axis. What are you graphing on the x-axis? What are you graphing on the y-axis? So in this case, we're going to have height of bounce over here and height of drop here. Okay, and this is our data. So each of these is going to be a little dot on this graph. First of all, we have to make a scale. The scale, the height of drop, we have to get up to 60. That's the biggest number, from 0 to 60. So we have to make a scale that we can fit up to 60. So this one I made by tens, okay? And therefore it ends here. The height of bounce only goes up to 22, so I can make a different scale to spread it out a little bit more, going by fives this way. So basically you got to be big, make the scale big enough so that you can take up most of your graph. You don't want the whole graph to be like over here, okay? No, you want to fill up as much of this as possible. Okay, so this will graph as much as possible. So each of these is a dot here. So 0, 0 is one dot. Okay, 620 is another dot. So 620 would be right over here. 930 or 620. I'm sorry, that's not the right. 620 would be 6 is over here. 6 is over here. 20 would be here, right? 930, so 9 is over here, 30 is over here. This would be another dot. 1240, so 12 is over here, 40 is over here. And 1750, 17 is over here, 50 is over here. And the last one is 22, which is up here, 60 is over here, over here. Now, these appear to be in some kind of nice curve. In this case, the curve happens to be a straight line. So that means there is a connection. There is some connection. Our mission is to find what is the connection. So let me go over here. So these are the points again. And so we can see that this connection looks to me like just about a straight line. Now, let me show you what not to do. What I'm going to do now, do not do this. Do not connect all the dots from one to the other. This one to that one, to that one, to that one, to that one. Don't do that. Basically, these dots tell you what kind of relationship is it. In this case, if it's a straight line, it means it's a linear relationship. And you connected with the best straight line you can. And you know that some of the points are on one side of the line, some of the points are on the other. And why are they? Well, because this is hard to figure out with the height of bounce. If you're looking at a ruler, you see a ball fly up, you're sort of approximating more or less. And sometimes you do a little too much, sometimes you do a little too little. So your errors sort of average out. So this is the way you do. You draw a line. Okay, now What you need to do next is find the slope of the line. The slope is a measurement of how steep this line is. And imagine yourself walking up from here to here. Two things happen to you. And again, you can start anywhere you want, okay? So you can start walking from here to here. So two things happen to you as you do. First of all, let me mark these points. This point and this point here. So I'm walking up from here to there. Couple of things happen. Number one is I start at this height and I go up. I have a rise. Sometimes you call it rise. Sometimes you just call it delta y. There's a change in y. How much is it? The y in this case? What's the change in y? Well, it's 30 minus 10. So the change in y, 30 minus 10 is 20. Also, as you start from here, and you have a run. This is called a run. You're going from 90 to 30. So the run, which we call delta x, is equal to 90 minus 30 is equal to 60. The slope of this line is just the delta y divided by delta x. So the slope, which you sometimes call m, is equal to delta y divided by delta x. And the delta y is 20 divided by 60, which equals 1/3. Once you know the slope, and if this is a straight line going through the origin, then the connection between these two variables, you can call one y, the other one x, is equal to the slope, that y equals the slope times x. Now, in our case, we don't have y, we have height of bounce. Height of bounce equals the slope, which is 1/3, times the height of drop, which is what graphing along the y-axis, along the x-axis, right? That's delta x. You notice this is the same as before. More or less, this is 1/3 of that. 1/3 of that approximately gives you that. Approximately, that's why you have these little differences here, because there's some error in measurement. It's hard to measure these things. But this is how you derive a mathematical relationship between two variables that vary linearly and go through the origin. Okay, so here you can see another calculation. In this case, I use just the bottom here. So from here to here is the run, and from here to here is the rise. It gives you the same numbers. It doesn't matter what 2 points you use. You get the same answer. Now, do not do this. Again, do not take 2 points that are very close to one another, like this one here and this one here or something. Spread them apart, like I did here. Another thing, do not do this. Do not take just points from here. That's these coordinates minus this coordinate, divided by this coordinate minus this coordinate. Don't do that. Do it from the line, okay? Because don't forget, these coordinates are not right. The line gives you the best results. All right, so let's do another example of this, a little more sophisticated example. Let's say we have a bunch of circles.
Call from Stan Kellican.
Yeah, I should have unplugged my phone. Sorry about that. I usually unplug my phone. I just didn't now. All right, so let's coming back to this. We have a bunch of circles, and I usually do this in class. I have groups of students who measure, first of all, the diameter of each of these circles, distance across, this is the diameter. So for this circle, it's 2 centimeters. And then the distance around, the circumference of the circle. I give them tape measure, they measure it. So in this case, for this circle, this is the diameter, this is the circumference. Now we're going to make a graph. This is the data for these 5 circles right over here. And one more circle here. We have a circle whose diameter is 0, its circumference is 0, right? Okay. So now what we're going to do is we want to find the connection between these. Well, I'm looking at the numbers here. No, I don't see a connection between looking at these numbers. So what do? Well, we're going to make a graph. Now, it doesn't matter in particular case which one you call the y, which one you call the x, but we're going to graph circumference here for a particular reason. You'll see it later. And diameter here. You could have done it the other way around. Okay, so this is our data, and we want to graph it. So just starting from scratch. First of all, you have to prepare a data table. All right, this is the table. Then you have to label horizontal and vertical axes with the same headings used here, the same headings here. We already said that this is going to be C, this is going to be D, diameter. And the units you're going to use. So in this case, centimeters. This will be centimeters. And this will be centimeters. Okay, that's number 2. Make a scale. In other words, you want to, on D, you're going up to 20, you want to make a scale so you can get up to 20. And you don't want the whole graph to be like in a tiny part of it. You want to use as much of this as possible. Going up on the circumference, you want to get as high as 50, so you'll have a different scale. All right? So choose an appropriate scale unit and number your axes. And then plot the points, as I did this before, and then finally draw a bar graph or a smooth graph or a straight line through your points, depending what the graph looks like. So we're not going to make bar graphs in this course, but here are the first couple of things. Again, we've labeled the axes. I'm going by 5s over here, and I can get up to 20. This way, I'm going by 10s, because I don't have to go as high. I can get, oh, you only need to go up to 20. Here, I need to get, I'm sorry, 50 going this way. Yeah, these, I reversed these numbers. This should be diameter, and this should be circumference. My mistake. So diameter goes to 20, circumference goes to 50. Okay. And now what we're going to do is going to make a graph. Each of these is going to be a dot. All right. So here are the points that I made for each of these dots. One of the points should be 0, 0. Okay. In other words, if I give you a circle with 0 diameter, it has 0 circumference, no? So that's the first point. And then these are all the other points. They appear, except for the last point, they appear to be going in a straight line. And again, don't forget, I usually do this in class with students. So some group of students messed up because all these appear to be in a straight line, except for that last point. So what we're going to do is we're going to ignore that last point. If somebody messed up, we're going to ignore that because it's way off. All of these are pretty good. Don't forget, you draw the line in such a way that there are some points above on the left side of the line and some points on the right side. In fact, I probably could dip this a little bit lower like that. Okay. Now that dip is important. That dip is important because this is good. This is going to be, we have to determine the slope of this graph. So again, we want to find out the connection between C and D. So we know the connection is going to be that circumference y is equal to mx. In our case, y is equal to circumference. M is the slope, which we're going to calculate in a minute, and x is d. So let's calculate the slope. Again, we choose 2 points fairly far apart. Usually you have to get the edge of a line. You can go past the data. So just say this is 1 point, could be another point, could be like over here or over here. This would be nice, these points. And again, if you choose these points, you're going to calculate what this is. What's the rise? Again, using the numbers over here. And what's the run? Using the numbers over here. Okay, in the next slide, I have this done a little more neatly. All right, so these are the 2 points I chose. So this one here, okay, the run, delta x, what we call delta x. I should have done this in red. Delta x is equal to approximately 13, this is 13 over here, and this is 4. So delta x is 9. Delta y is 40 minus 12. This is 12 over here, and this is 40. So delta y is 28. All right, the slope therefore is going to be delta y divided by delta x. You have it here. And again, do not use data from here to calculate the slope. Do not use that. You can say, oh, I'm going to just use this and this. No, please don't. Do it from the line of the graph. And then for delta x, I'm going to use this and this. Even though it's not absolutely wrong, but it's not the best way to do it to get the closest results. You find the slope using the line, not the points that you did, because the points could be off, like this one here. Okay, like this one here is a little bit off. So it's better to do this. So it turns out that the slope is 3.11. So what's the connection between these two? Well, let's see if I have that. No. So I'll write it here. The circumference equals 3.11 times the diameter. Now, you probably caught on already what this 3.11 here. It's probably learned back in 5th grade that circumference is pi times diameter. So you should have gotten 3.14, but you didn't. You get pretty close, basically, but you didn't quite get it, and you rarely get the exact number. So the next thing you do in the lab is you find out, okay, I'm supposed to get 3.14. I got 3.11. How close is that? Is that, the percent? So this is what you do. You find the difference between these two. In other words, 3.14 is what I should have gotten. 3.11 is what I got. You divide that up by what you should have gotten. And to change, this will be a decimal number. And to change this decimal number to a percent, you just multiply by 100. So in this case, if you do this, you get approximately 1%, which is, you're never going to get, in a real lab, you're never going to get something this close. Usually something on the order of 10% or less is pretty good. And that means you almost got the number. I mean, very, very good. 3.11, 3.14, they're very close together. So let me see if we got anything else here. No. So basically, what is slope? For example, if this line here, if you wanted to calculate the slope, which is delta y over delta, and this, say in math, this is y, this is x. But in physics and science, this is not y and x. These are other things that represent what you graph on the y-axis and represent what you graph on the x-axis. So to find the slope of this, again, you pick 2 points. Let's say I'm going to pick this point and that point. So this point is 70 and 30. So delta y is 70 minus 30. And delta x, so this is 0, and this is 40. So delta x is 40. 40 minus, yes, my delta x is 40. And by the way, 70 minus 30 is also 40. All right, it just turns out that the slope is 1 in this case. Now, but this is a little bit different. This is a straight line, yes, but the line does not go through the origin. If it goes through the origin, then y is equal to the y, whatever you're graphing on the y-axis is equal to the slope times whatever you're graphing on the x-axis. But if it doesn't go to the origin, you have to add that number. We call it b. The number at which this crosses the y-axis. In this case, that's 30. So in this case, we have y is equal to, and I'm going to make this a different color because the slope m happens to be 1. 1 x plus 30. So y is equal to x plus 30, basically, would be the equation of this line. So this is basically the one we did below. It's a multiple choice question. The slope of that line happens to be 1, and that's how you calculate it. Okay, now let's do one like that. Let's say I'm going to give you these variables. Can you look, by looking at it, can you figure out how they're connected? What equation connects these numbers? Well, probably if you looked and played with this for a while, you probably eventually figure it out because it's not complex. But again, if you did the graph that's using these 5 points, you would find you get a straight line. And you were to find the slope of this line, you would find the slope is 2. And it crosses the x-axis at 3. So the equation is y equals 2, which is the slope, x plus 3. And this is the y-intercept 3 over here. So we are going to apply this to a real case. We know that we can measure temperatures in this country in degrees Fahrenheit or degrees Celsius. So basically, that's what we're going to do. We're going to have 2 thermometers, 1 Fahrenheit, 1 Celsius. And we want to see how the Fahrenheit is connected to Celsius, an equation that connects the two. So we measure a bunch of temperatures with the Celsius thermometer. Here they are. And we measure a bunch of temperature with the Fahrenheit thermometer. Here we are. And then we're going to do a graph of Celsius, of Fahrenheit over here, and Celsius over here. Again, we make a scale. We got to get on the Fahrenheit. We got to get all the way up to almost 220, right? 212 is the highest number, so we can go by 20s and can get up to 220. On the Celsius, we only need to get up to 100, so this scale is enough. And it looks something like this. The graph will look something like that. I'm going to show you a little bit better version of it. So here is the numbers again, the data. We have to label the axis, put in the scale in each direction, and that'll be the next slide. One thing we got to be aware here is that this number, this point here is 0, 0, but we have negative temperatures, so we got to have room on this side for negative temperatures. So this is going to be 0, and this is going to be the next number, next number, next number, right? That's this point here, but we have to have negative temperatures. So this is the kind of scale I chose here. So every one of these is a dot on here, a dot. Okay. Save a little time. I'm just going to go ahead and show you where the dots are. They are over there. And therefore, for example, 0 Fahrenheit and Celsius is minus 20. So that's this dot here. The last dot up here is 212. We're just a little bit off the paper here. 212 and 100. So that's the last dot. So these appear to be in a straight line, and what you do is you draw the best straight line right through all of them, including those negative numbers. Okay, and you notice again, a couple of the points are on this side, a couple of points over here are on this side of the line. And this is probably, various mistakes you could have made in reading the thermometers, possibly. So the next thing to do is to find the slope of this line. All right, and again, for a slope, just pick any 2 points. For example, I could pick this point and that point, or I could pick this point and they say this point here. I'll show you in the next slide which points I actually took. Okay, it's over here actually. So I'm going from here to here. All right. So you're going from 80 to 160. So the rise is 80 degrees Fahrenheit. What's the run? You're going from 72 to 30. The run is 42. Okay. So what's the equation? Well, the slope, right? The slope I calculated right here, 80 divided by 42. And don't forget you put the units here because now the slope has meaning. There's, for every Celsius degree, there is 1.2 Fahrenheit degrees, so 1.8 degrees Fahrenheit per degree Celsius. That's what this is saying. So the temperature increases by 1 degree Celsius. That's like almost 2 degrees Fahrenheit, almost 2. So again, looking at the journal equation, y equals mx plus b. M is 1.8. I want to make this a different color. So the slope is 1.8. We're going to put that in for m over here. This is the y-intercept, and you can see the y-intercept goes at around 30. This is 40, this is 20, it's a little bit more than 30. Well, actually, it's supposed to be exactly 32. So this is the connection that connects. You can convert from Fahrenheit to Celsius by using this equation here. All right, so all of these equations, all of these examples that we did, we always did it with examples that gave us a straight line on the graph. So let's look at one that doesn't give you a straight line. And what do we do about that? All right, so let's take a look at this one. We know we graphed, we already did the circles, right? No, okay, no, we didn't do the circles. That's my other class. No, we did the circles in terms of circumference, but what we're going to do now, we want to make a graph using experimental data. In other words, we're going to measure all these things. We're going to measure the diameter of each circle and the radius. And also, we're going to measure the area of the circle. How do you measure the area of a circle? Well, what you do is you draw the circle inside a grid like this, and you count the number of grids that are inside. Yeah, I know it's hard, and it's a long process. And you have to approximate how many grids are over here. I don't know. I could sort of approximate how many here are in these corners, because, but that's the area. You do this for each circle. All right. Since I've had my vacation here, I had lots of time to do this, so I did it. I drew circles inside these grids. I counted approximately the number of grids, and I got these numbers. And also another number that comes up here is 0, 0. Okay. In other words, a circle, this one here, whose radius, this one here, whose radius is 2, the number of squares that fit inside is 12. Okay, etc., for all these different circles. So again, what we're going to do is we're going to make a graph. And one thing about graphs is we're going to find that the graph that we make of this versus that is not a straight line. I'll show you that in a second. But first of all, let me just show you what do you do. If the graph turns out not to be a straight line, then we can assume that it's possible. It's possible. It doesn't have to be that if it looks like this or like this, it goes away from a straight line. That means this could be the possible relationship between the y and the x. That y is equal to some number k. We don't know what k is. We have to find it from the graph. We'll show you how in a minute. Times x raised to some power, like 1, 2, 3, 4. Or if it curves down like this, that means this power is less than 1. If it curves up like this, that means this power is more than 1. You can see that here. Now, there's another way to do this using logs. We're not going to do that today, possibly at another time. But here we have the circles. All right. We count the number of squares inside. We get these numbers. And one more piece of data over here. And we're going to make a graph of that data. Okay. First of all, we make a scale. The radius is pretty easy, goes up to about 10. All right, then it goes by ones here. But the area goes to 250, so we got to go by actually by 40s. Each box is like 40 more, and then the 250 will be up here. I think if you put in by 20s, you're going to go off. So you need about 50 here. So this is the scale we're going to use. We label our axes, and we make the graph. In other words, each one of these is going to be a dot here, and here are the points. Okay, using the 0, 0, we have, for example, this point here is 7. That's this over here. 7 and 160, which is over here, or in the middle. So these appear classically to be what we're talking about, not a straight line graph. Let's see how good I can do this. Okay, so you can see what the shape of the curve is. So this tells us, okay, probably this is not a straight line. How do we find the connection? Well, probably it is of the form y is equal to k x raised to some power, okay, where y here is area, is equal to some number. We don't know what this number is. We've got to figure it out. X raised to some power. And this power is going to be bigger than 1. This power is going to be bigger than 1. Okay, so for example, what's bigger than 1? Well, maybe it's 2. That y is equal to some number times x squared. We're going to make that guess that this is the connection. We don't know right now it's for true, but it will be true if we make a different type of graph. Not a graph of area versus radius, but a graph of area versus radius squared. Okay? So how do you make a graph of x versus radius squared? Not that. You basically take these radii, these numbers, and you square them. All right? So 0 squared is 0. 2 squared is 4. 4 squared is 16. 7 squared is 47. 9 squared is 81, not 91. 81. These stay the same. These don't change. Now we're going to make a graph of area versus radius squared. If we guess correctly that the relationship is x, which is radius to the second power, we should get a straight line. So let's do it. So 0, 0 is 1 point here. 4, 12. So we go 4 over here. 12 is over here. 16, 50. So you get 16 is over here. 50 is right over here. 47, 160. 47 is right over here. 160 will be right in the middle here. 81, 81, right? 81, 250. It's going to be like right over here. Guess what? We lucked out. We guessed right. It is a straight line. I could probably draw a better curve here. Okay, that looks pretty good. And again, we got almost perfect. And the thing is, when we were counting those squares, we could have made little mistakes. We approximated how many squares. For example, you can see a little mistake here. You can see a little mistake here. These, we seem to have gotten these little circles pretty much on the nose. So we want to know what's the connection between this and this. It's a straight line. So basically what that means, y, it goes through the origin, equals the slope of that line times x. Y is area. X is radius squared. So our mission is to find m. Okay? And m, of course, is the slope of this line. So we go back to the old way we were doing it. We pick 2 points along here that seem to be, for example, I could pick this point, and Well, I could pick the bottom point here because I'm looking for what goes right on the corner of a line. I could pick these 2 points. And in the next slide, I'll show you which I actually picked. Okay. Yeah, these are the 2 points that I picked. And so, for example, the rise here, delta y, is 260 minus 80, right, or 180. Delta x is 90 minus 30, which is 60. Of course, the slope, now delta y over delta x, is going to be 180 square centimeters divided by delta x, which is 60, also square centimeters. So what happens, the number we get here will have no units. Usually the slope very often has some kind of units associated with it, but here the units cancel off and you get just 3. Very simple, 3. So we can say this, hey, area of any circle equals 3 times the radius squared. Now go back to 7th grade. What's the formula you learned that? The area of a circle is equal to pi r squared. So this number that we got here for slope should have been 3.14. We're a little bit off, but we're pretty good. Let me tell you, this is pretty good. This should have been 3.14, but we got 3. What percent error is that? Well, 3.14 minus 3 divided by 3.14 and times 100. Oops, times 100. So 3.14 minus 3 is 0.14 divided by 3.14. Let me see what is that. I got my calculator here. 0.14 divided by 3.14 is equal to 0.04. If you multiply that by 100, we get 4%. And of course, this would be very good results because again, it was hard to count those squares, right? You had to approximate. But I'm good at that. I'm good at counting squares. So I got a pretty good job. But if you actually did this, and I actually do this in class, I have students count the squares for those circles. I draw them on the grid paper. And of course, we're much more off than this usually here. So let's go to a physics example of such a thing, which you're going to be doing in a couple of weeks. You're going to be doing another example this week, which I'm going to get to in a minute. But in a couple of weeks, you're going to be doing, you're going to be looking at a falling body, an object that's falling. Now, I touched upon this, that the equation, right, the distance something falls is equal to 4.9 t squared experimentally. Galileo, first of all, figured that out, that freely falling bodies, first of all, they all fall at the same rate, and this is the distance they give in a certain amount of time. So basically, let's say you didn't know that. So you do an experiment where you actually measure the distance an object falls and time it. All right. So basically, you're going to make this data versus this data. You make a graph of that. All right. So I think in the next slide, I make a graph of that. Here it is. Again, I look at the data here, and I make a scale here. The time here goes from 0.28 to 0.5, so I can use this scale here. The distance goes from 0 to 1.2, so I can use this scale over here. This is in meters. And each one of these is a dot, all right? So this is the dots that I put on here. And, oh, look at that. No, it's not quite right. It didn't quite make a straight line. It was pretty close, but it's not a straight line. It turns out if you actually draw the curve, you see it goes up like that. Okay, it seems to be one of those y is equal to x, kx raised to some power. Yeah, that's because of this. Okay, but let's say you don't know that. Galileo didn't know that when he did the experiment, but he saw this. So basically, it's not a straight line. You're going to guess it's curving up. So the power here is going to be, power here is going to be bigger than 1. So let's assume it's 2, which means y equals some number times x squared. And therefore, if you make a graph of this versus these numbers squared, which I have over here, what you do is square this, you get that, square this, you get that. And now we're going to make a graph of this versus time squared. Not time like we have here, but time squared. And here it is. Here's that graph. It is absolutely a straight line. Okay. Maybe a little bit wider. Okay. So our mission is to find the slope of this line. All right. Don't forget, we're finding the slope because we're saying that y is equal to k x squared. In our case, distance is equal to k times time squared. And we want to figure out what's k. So we have a graph of this versus that, gives us a straight line. K is going to be the slope of this line. You have to pick 2 points somewhere, find the rise, run, find the slope, and I have that in another slide. Okay, so these are the points that I picked. This is 0, 0. This is this divided by that. The slope basically is going to be this number divided by that number. Okay. And you can see the slope turns out to be 4.74. Okay. Now there's an equation in this case that connects these two, that the distance, I have S here, but this could be D, equals 1/2 gt squared, where g is the acceleration due to gravity, something we'll be studying pretty soon. But anyway, g is a constant of nature, and it's 9.8. So basically, the number here is 1/2 of that. We got this to be, but we should have gotten 1/2 of that, 4.6. But we got pretty good 4.73, which means we predicted that g is going to be equal to that number. Okay, the slope is equal to, the number in front of t squared is the slope, is 1/2 g. We found the slope to be 4.9, or almost 4.9 over here, 4.74. So that is half of g. So what is g? Well, g would be twice that, which again is 4.74 times 2 is equal to 9.48. Okay, and we should have gotten 9.8. So again, calculate the error, 9.8. It's going to be a little bit bigger now because this is actually data from a real experiment. Divided by 9.8. In other words, this is basically what you should have gotten, but what you actually got divided by what you should have gotten, and you multiply that by 100 to get the percent error. And this is probably around 10%, which is normal what you get around here. So let's go to next week's lab. Next week's lab, we're going to go directly to that. Okay, I gotta skip some slides here. Okay. So next week's lab is going to be like the lab like the one you just did. So I'm going to go over it step by step. So first of all, what you're going to do is it's called the pendulum lab. You're going to have a pendulum, which you will you can change the length of the string that you're holding it. So let me show you the simulation you're going to use. It's right over here. So I can change the length of the string over here by moving this. And what I want to find out is, if I go like this and I let this go, it swings back and forth. The time for it to swing back and forth is called the period. Okay? And we want to know, how is that period, that means the time to go back and forth, related to the length? Or is it related at all to the length? We can use a ruler here by measuring the length for various, we can have various different lengths. We can change the length to this, to this, to this, etc. And for each one of those, we just let it go and we time it. We use stopwatch. You can actually have a stopwatch over here, and I have one over here. And you time it, let's say, for 10 oscillations, 10 swings back and forth. And then the time for one swing, or the period, is just that number divided by 10. All right? So let me stop this. So that's the lab. So we're going to collect data. Okay, we're going to collect data you do in that lab of the period. We call that T, the time for one oscillation, versus, well, we're going to guess that length. Okay, the length, it matters. Length affects it. And the question is, how are they related to one another, if that's true? So we make a graph of T versus L. And when we make the graph, this is some sample data, we find something very strange that I haven't met. It's not a straight line, and it's not one of those curves that we've been talking about, where it goes up like this, but we have the opposite. It goes like this. What does that tell us? Well, that tells us it's possible that they're connected by this type of equation, that the period, in other words, these numbers here, versus the length is equal to some number times the length raised to some power, where A is going to be less than 1. Less than 1. We know that because it curves this way as opposed to curving that way. Now, let's see. That's a number less than 1. Very often you get a half as that number. So we're going to guess that it's a half. A half means square root of L. So what we're guessing is that T is equal to K times the square root of L. Now, if we square both sides, we square the left side, we get T squared equals K squared. This squared is just L. We get this equation. So if we're right, if we make a graph of T squared versus L, if we're right, we should get a straight line, and the slope of that line will be this number squared that's in front of the. It won't be K, it will be K squared. The slope will be equal to K squared. So if you do that, and you're going to do that in the lab, all right, you will in fact find that you get a straight line, and I'll show you that in the next slide. Here it is. See, I'm using different data here. This is the period, this is the length, this is the period squared. Okay, I just square all the times here. 2 squared is 4. This is about 2 squared also. You get a straight line. Oh, wonderful, wonderful, great. I love straight lines because I know how to proceed from now on. Okay. So to find the connection between T squared and L, all we got to do is find the slope of this line. Now, it turns out, let me go back to the previous slide. I should have done that before. It turns out that the connection, we'll find later in the semester, that the period and the length, this is supposed to be the length over here, is related by this equation. The period is 2 pi square root of L over G, where G is the same G we we found before, it's 9.8. It's one of the constants of nature. Okay. If we square both sides here, well, t squared is t squared. 2 squared is 4, pi squared is 4 pi squared. And you square this, you just get L over G. This is L over G. Okay? That means that the connection between this, if you make a graph of t squared versus L and find the slope of that, this is the slope of that. If it gives you a straight line, which we already know it does, right? Gives you a straight line. Therefore, t squared, so the slope is going to equal whatever number we get, call it m, but that m is going to equal to 4 pi squared over g. It's going to be the number here in front of L. L. So we have to calculate the slope, set the slope equal to 4 pi squared over g, and so you can solve that equation for g because we know what we're supposed to get for g, 9.8. So, right, g is going to equal to, if you solve this, this is the slope, g is going to equal to 4 pi squared divided by the slope. And then, again, you have your true value, to find the percent error, your true value minus your experimental value, divided by the true value, which is 9.8 times 100, when you find g. And I think I do these calculations here, all right? So these are my calculations for that. All right, I chose this point and that point. And this is just 3 minus 1, which is 2. And this over here, delta x. So this is delta y, this is delta x. This is a half, because this is 0.75 divided by 0.25 over here. So this is delta x. This is delta y. Very easy to calculate the slope, right? It's 2 divided by a 5. It's 4. Slope is 4. Okay. So now, right, we're going to use this equation to calculate what g is. Let me see. I think I have it here. Here it is. Okay. All right. So the slope is 4 for that graph. Therefore, this 4 pi squared, which is the slope, is equal over g equals the slope. So basically 4 pi squared over 4, which is the slope, equals g. The 4's cancel here. So g is just pi squared. Okay. Now what's pi squared? It's approximately 10. So a percent difference using this equation here is our true value, which is 9.8. We're supposed to get 9.8. We got 10 divided by the true value, 9.8, and multiplied by 100, you get approximately 2% error. Okay. And that's basically this coming week's lab. And I think I did a good job here. So,